Hey everyone, and welcome to today's Explainer. I am absolutely thrilled you're tuning in. Today, we're taking the fundamental laws of classical mechanics and breaking them down into highly digestible, totally exam-ready building blocks. Now, look, if you've ever felt overwhelmed by physics, and let's be real, who hasn't, do not worry. We're going to build this up logically, visually, and super intuitively. It's going to be great.
Here's our roadmap for the Explainer today. We're covering 1. Force and Newton's laws. 2. Momentum and impulse. 3. Understanding friction. 4. Uniform circular motion. And finally, 5. Essential exam strategies. Let's get right into it.
So what actually makes things move, or stop moving? I know, it sounds almost too simple, right? But the answer to this exact question is what unlocks the entirety of classical mechanics. It's like a giant puzzle, and this is the first piece. Let's find out exactly what's going on behind the scenes.
Section 1. Force and Newton's laws. The basics of physics.
All right, let's kick things off with a formal definition. A force is essentially an external agent. Think of a push or a pull from a spring. It's something that changes, or even just tends to change, the state of rest or uniform motion of a body. And crucially, we measure this in newtons. You'll see that denoted by a capital N. To put that into perspective, 1 newton is the exact force required to accelerate a 1 kilogram mass at 1 meter per second squared. But the real key takeaway here, it absolutely has to be an external agent.
So what exactly can a force do? Well, it can change an object's speed, it can change its direction, or it can literally change its physical shape. But I really want you to focus on that last bullet point right there. A force produces acceleration. That's the big one. That is the key concept we're going to be chasing throughout this entire explainer. You see, acceleration is the undeniable footprint that an unbalanced force leaves behind. Now, you really can't talk about force without also talking about inertia. Inertia is just an object's natural, stubborn tendency to resist any change to its current state. On the slide, we're comparing two types. Inertia of rest basically means a body completely resists moving if it's currently still. On the flip side, inertia of motion means it resists stopping or changing direction if it's already moving. And here's the secret to the whole thing. Inertia is deeply, fundamentally tied to mass. The greater the mass, the greater the inertia. Think about trying to push a tiny toy car versus pushing a real full-sized heavy car. That heavy car stubbornly wants to stay exactly as it is unless it's explicitly forced otherwise.
Which brings us directly to Newton's first law, also very appropriately known as the law of inertia. Honestly, think of this as the ultimate rule of laziness in the universe. A body will basically just remain at rest or keep moving in a uniform straight line unless it is acted upon by an unbalanced external force. This law is what qualitatively defines what force actually is, and it introduces us to the concept of the inertial frame. But the most practical takeaway for us? If the net external force on an object is zero, its acceleration is zero. Period. Guaranteed.
Section 2. Momentum and impulse. Mass in motion. Now, it's incredibly interesting how we actually quantify all this movement. We use something called momentum, which is represented by a lowercase p. This is the quantity of motion possessed by a body. And the formula? It's beautifully simple. P equals mass times velocity. Also, keep in mind it is a vector quantity, which means its direction is the exact same as the velocity. So if you've got a really massive object or an object moving incredibly fast, boom, you've got a much larger momentum. Building right on top of that, we arrive at Newton's second law. The formal definition states that the rate of change of momentum is directly proportional to the applied force. But if we're dealing with a constant mass, this boils down to the absolute powerhouse of Newtonian mechanics. F equals ma. Force equals mass times acceleration. Seriously, this simple little formula is the engine behind solving nearly every classical physics problem you are going to encounter. It completely proves that force is the direct cause that produces acceleration.
Let's take a second to look at this in the real world, because it's actually pretty cool. Think about airbags deploying in a car crash, or a baseball player catching a super fast pitch by pulling their hands backward, or even the shock absorbers in your car. What do all of these things have in common? They extend the time of an impact. By increasing the time interval of the collision, you drastically reduce the deadly peak force that the body actually experiences. It's literally physics saving lives every single day.
And completing our classic trio is Newton's third law. For every action, there's an equal and opposite reaction. But hey, pay really close attention to this critical detail. Action and reaction forces act simultaneously on different bodies. They never, ever act on the same body. Because of this, if the external force on a whole system is zero, the total linear momentum remains totally constant. This brilliant principle of conservation is the exact reason why a gun recoils when fired, and it's literally what makes rocket propulsion possible in the complete vacuum of space.
Section 3. Understanding friction. Opposing motion.
Okay, let's draw a hard line between the two main types of friction that oppose relative motion. First, we have static friction. This acts when a body is completely at rest, basically resisting that initial push. Then we have kinetic friction, which kicks in once the body is actually moving. And here is a massive pro tip for your exam, so definitely remember this. The coefficient of kinetic friction is always less than the limiting static friction. What does that mean in real life? Well, it means it always takes considerably more force to start moving a heavy object than it does to just keep it moving once it's already sliding along.
But there's a third crucial type we absolutely have to consider, and that's rolling friction. Rolling friction is much, much smaller than sliding friction. Why is that? Well, because the microscopic deformation of the surfaces in contact is significantly less when something is rolling. This simple little physics fact is exactly why the invention of the wheel was such a massive game changer for humanity, and it's why we use ball bearings in nearly all moving machinery today to drastically minimize surface resistance.
Section 4. Uniform circular motion. Continuous curves.
So when a body moves in a circular path with a constant speed, its velocity is actually changing continuously. Wait, why? Because its direction is changing at every single point along that circle. So the crucial point we need to understand is this. A change in velocity means there must be an acceleration, right? And therefore, there must be a force. We call this the centripetal force. It's the inward force, always directed toward the very center of the circle, that's required to keep that body from just flying off in a straight line. And you can calculate it using the formula F equals mv squared divided by r.
Let's apply this to a real-world engineering challenge like building roads. When a car takes a turn on a flat, level circular road, it has to rely entirely on the friction between the tires and the asphalt to provide that inward centripetal force. If that friction fails, say on an icy day, you skid right out. But look at the banked road. By intentionally tilting the road at an angle, which we call the banking angle, engineers creatively use a component of the normal force to help provide that necessary centripetal force. This is brilliant engineering because it dramatically reduces our dependence on friction alone, completely prevents deadly skidding, and allows for much higher safe speeds on things like highways and racetracks.
Section 5. Essential exam strategies. Trap avoidance.
You know, test makers absolutely love to set traps, and I want to make sure you dodge every single one of them. First trap, confusing centripetal force, which is very real and acts inward, with centrifugal force, which is actually a pseudo-force observed only from a rotating frame. Second trap, forgetting that friction always opposes relative motion, always. Third, and guys, this is a really big one, treating action-reaction pairs as if they act on the same body. They don't. They never do. And finally, ignoring the vector nature of momentum. Direction matters just as much as magnitude. Do not fall for these traps. All right, here's your ultimate cheat sheet for classical mechanics on exam day. We've got momentum, Newton's second law, impulse, centripetal force, static friction, and that all-important formula for the banking angle. I literally want you to mentally screenshot this table right now. Seriously, burn these formulas into your memory, because knowing these inside and out by heart is going to save you so much precious time when you're sitting down for your exams.
Let's take a step back and connect all the dots here. Why did we spend all this time on these specific fundamental concepts? Because having a rock-solid understanding of force analysis and drawing accurate free body diagrams is the absolute gateway to everything else. If you master what we covered today, you immediately unlock the ability to tackle work, energy, and power problems. It's incredibly crucial for understanding rotational motion later on. Simply put, these principles are required for absolutely everything else you'll do, even stretching way out into modern physics applications.
Which brings us to our final question for the day. With these laws of motion now forming an unbreakable foundation of classical mechanics in your mind, are you ready to master modern physics? Because you now have the tools to do exactly that. Take these building blocks we've discussed, practice drawing those free body diagrams, and really apply them. Keep that curiosity burning, keep solving those complex problems, and I will see you next time as we continue to explain the absolutely fascinating mechanics of our universe.